This is Applied Calculus, Section 2.7, Marginal Analysis. We begin this section with some definitions, and note we're acknowledging that x is the number of units of a product being produced over some time interval. If we are given a cost function, we can find a marginal cost function by using the derivative. And this is true for the revenue function. Its derivative will be the marginal revenue, and the same is true for profit. Its derivative will be marginal profit. And the question that we should get is, what does marginal mean? Well, marginal means how does cost, profit, or revenue change when production is increased by 1? And one thing to keep in mind is that marginal gives us an approximation, not the exact change in cost, revenue, or profit. And if we wanted to calculate exact, then we would use the function itself, not the derivative. For example, the exact change in cost would be c of x plus 1 minus c of x. No derivative being used here, and it's going to be a slightly different answer than marginal, but they will be very close, and that is why we use the derivative. It is a good approximation, and it is an efficient way to get the approximation. So here we have an example, and as we work this out, you'll see how well the marginal cost approximates an increase in the production level by 1. So part A asks that we find the marginal cost function. We were already given a cost function, and if we read the top here, it says a company manufactures fuel tanks for cars. The total weekly cost in dollars of producing X tanks is given by this cost function. And part A, we're going to take the derivative of c prime of x, and that's how we find the marginal cost function. The derivative of a constant is 0, so the 10,000 is gone. Derivative of 90x is 90, and derivative of negative 0.05x squared is negative 0.1x. We're done. We have our marginal cost function. Part B asks that we find the marginal cost of production when we are at 500 tanks per week. So marginal cost is C prime, X is 500, and when we plug this in, we end up with $40. Part C asks that we interpret the results from Part B, and what this says is the production of the 500 first fuel tank will increase the weekly cost by $40. Finally, Part D asks that we calculate the exact cost difference for the 500 first item. And here that means we're going to calculate C of 501 minus C of 500. Again, I want to emphasize these are not the derivative functions. This is the original cost function. So we're going to type in the cost function, 10,000, plus 90 times 501 minus 0.05 times 501 squared. Hit the enter, and we get $42,539.95. C of 500 gives us $42,500, and we have a difference of $39.95. And when we look at this, we say, yes, the marginal cost gave us a very good approximation for the difference in cost by producing one more, and it was a quicker, more efficient way to get the answer. So here's a visual representation of what the marginal cost is calculating. So the blue curve is the cost function, and the red line is the tangent line, and derivative calculates the slope of the tangent line at a point, and we see that that slope gives us the direction of how cost is changing. So it gives us a quick, easy way to find how is cost changing from one point to the next. And that's why we use marginal cost to approximate the exact cost of producing one more. So here's the next example. Try this on your own. Pause the video, work it out, then unpause to see if you get the same answer. So the problem reads, the total cost of producing X bicycles is given by the cost function below. C of X is 10,000 plus 150X minus 0.2X squared. Part A says find the exact cost of producing the 121st bicycle. So for part A, we're going to do C of 121 and minus C of 120. So C of 121, we get $25,221.80. And C of 120 gives us 25,120. And we see that the difference is $101.80. So this is the exact cost of producing one more bicycle when production levels are at 120 bikes per week. It says use the marginal cost to approximate the cost of producing the 121st bicycle. So we want to approximate it by using C prime of 120. It's important to remember the relationship between the exact difference and the marginal cost. The marginal cost is always being evaluated at one less than the exact 121st that we're approximating. So first, let's write the marginal cost function. The derivative of 10,000 is 0. The derivative of 150x is 150. And the derivative of negative 0.2x squared is negative 0.4x. And now C prime of 120 is 150 minus 0.4 times 120. That gives us $102. So once again, we see this is a good approximation. It gave us a fast and efficient way to get the answer for what is the cost of one additional bicycle when production is at 120 bikes per week. So here we have an application problem. This is going to tie in cost and revenue and profit and marginal and exact and everything together. We begin by reading the problem. A company's market research department recommends the manufacture and marketing of a new headphone. After suitable test marketing, the research department presents the following price-demand equation. Now, this is not the format that we're used to our price-demand equation. So the first thing I want to say is rewrite it in P equals form. Price equals a function of X, because that's the format we need to generate our revenue function. So P equals X minus 10,000 all over negative 1,000. And we can simplify this to P equals negative 0.001x plus 10. Or if we like the positive in front, P equals 10 minus 0.001x. So now we have it in P equals form. This is the format we can use to generate a revenue function. Part A says find the domain of the function defined by the price-demand equation. So we have our price demand equation. We know that price has to be greater than or equal to zero. We would never charge a negative number for price. That would be us giving away money. We'd say, here's our headphones and let me pay you. No, at the very least, we would give it away for free for people to test it out, but we wouldn't give it away for free and pay them to take it. So we want P to be greater than or equal to zero, which means solve for this price function when it is greater than or equal to zero. 10 minus 0.001x greater than or equal to 0. We can now add 0.001x to both sides. That gives us 10 is greater than or equal to positive 0.001x. We want to multiply both sides by 1,000, or you can say divide both sides by this decimal, because our goal is to get x to be 1x. And this tells us that x, which is the production level, is going to be between 0 and 10,000. Because you would not be producing negative headphones. That doesn't even make sense. So that takes care of part A. Part B says to interpret the marginal cost function. So we have our C of x. C prime of x is going to be equal to the derivative of C of x. C prime of x is the derivative of C of x, and the derivative of a constant is 0. The derivative of 2x is 2. So from here, we see that the change in cost of production is equal to 2, a constant. And because we don't see any x variable in the marginal cost function, that means the cost of production will always increase by 2, no matter what the x value is. And the x value is our production level. So that means the cost will always increase by 2, no matter how many headphones we are producing. So here we have part A, and for part B, C prime of x equals 2, cost of production, or cost of producing one more, always increases by $2. Part C, find the revenue function as a function of x and then find its domain. Part C, R of x is equal to x times the price function. Notice I use a little p of x for price. The capital P of x is reserved for profit. So for part C, we have the revenue function is 10x minus 0.001x squared. And its domain is the same as the price function. You can take each factor of the revenue function and set it greater than or equal to 0 to come up with the domain. And the domain we see matches what we have for the price function. Part D says find the marginal revenue for x equals 2,000, 5,000, and 7,000. Interpret the results. So marginal revenue is r prime of x. And if we take the derivative of each term, we get 10 minus 0.002x. And we want to evaluate R prime of 2,000, R prime of 5,000, and R prime of 7,000. So I'm going to use my calculator to do this in a quick way. Let's go to y equals. We will type in 10 minus 0.002x. I will go to second and table setup. I just want to make sure that my independent variable is on ask and hit enter. And then second, the graph button opens up the table. I will use the delete key to delete out the x values that were there. And I'm going to type in the x values I want plugged into my marginal revenue function. And we get 6, 0, and -4. And the interpretation is producing one more headphone when production level is at 2,000 increases revenue by $6. And you would write similar statements for R prime of 5,000 and R prime of 7,000. When production levels are at 5,000, producing one more changes revenue by 0, so we get no benefit from it. And when production values are at 7,000, producing one more headphone decreases revenue by $4. So why would revenue decrease by $4 by producing one more? Well, maybe you're paying someone overtime, and that overtime increases the cost of producing the headphone more than you're able to sell it for. So you end up with a loss at that point, and that means that the business model needs to be uh, reviewed and modified so that doesn't happen. Part E says to graph the cost function and the revenue function in the same coordinate plane. Find the intersection of these points on the graphs and interpret what it means. So here we see is the revenue function, and here is our cost function. And we talked about this earlier in the year that when cost equals revenue, that is known as break-even analysis. That means no money is made, no money is lost. But for the parts of the graph where revenue is higher on the y-axis than cost, that's where you experience profit. And for parts of the graph where the cost function is higher on the y-axis than the revenue, those are locations of where you experience loss. So this green range right in between, this is what we're interested in. We want to know what are the different profits we can experience in that level. Part F says find the profit function and its domain and sketch the graph of the function. So we want to recall that profit equals revenue minus cost. We will call the profit function P of X, and notice we're using a capital P because the price function is lowercase p. And now we just have to recall our revenue function. And we see we have a 10x minus 2x, so that gives us 8x minus 0.001x squared minus 7,000. So the domain of the profit is going to be a combination of the domain of the revenue and the cost. So we see that the domain is also going to be between 0 and 10,000 because that's where the domain of the functions that make up profit exist. And now we're asked to sketch a graph. So we're going to go to y equals. We're going to go 8x minus 0.001x squared minus 7,000. After entering the equation, press the window button. I have the window set up here already. X values go from 0 to 10,000 because that's the domain. And then I said to put tick marks at every 1,000. Y values I have set from negative 10,000 to positive 10,000. And I did that because I saw that negative 7,000 was a potential for loss if we produced nothing. We would start off at negative 7,000. So I went from negative 10,000 to positive 10,000 on the y-axis and counted by 1,000s. If this graph does not look right, I can add more space on the y-axis. Now that my window is my drawing area, now that it is set up, I will hit the graph button. And it looks like that was a good maximum. I set 10,000 as a maximum. I'm almost at the top of the window. And I have my profit function. So I generated the graph in the calculator, and this is what we got. Just looking at the graph, we can see that the profit function crosses the x-axis at about the 1,000 unit mark, and then it's above. This is where we're making money all through here, and then it crosses back again at 2, 3, 4, 5, 6, 7. So it looks at the 7,000 mark. We're back at making zero profit. So anywhere between 7,000 and 1,000 headphones, we should make money. Now, part G asks that we find the marginal profit, which is the derivative of profit. And we're going to get 8 minus 0.002x as the derivative. And then we're asked to calculate p prime of 1,000, which gives us 6. And if we look at this, because we're talking about derivatives, at 1,000 there is a tangent line here, and we see the tangent line is moving up. So that means that profit is moving up. So the 1,000 first pair of headphones increases profit by $6. All right, we want to do this again for 4,000. P prime of 4,000 gives us 0. 2,000, 3,000, 4,000 we see is right up here at the top. That gives us a horizontal tangent line. So the change in profit is at 0. So the 4,000 first item is not going to increase profit at all. And if we evaluate 6,000, P prime of 6,000, we see that's right here. Well, the tangent line is in a downward slope. That means that we expect to lose profit moving forward. If we calculate this in our marginal profit function, we end up getting -4, which means that the 6,000 and first item causes us to lose a profit of $4. So the next topic in 2.7 is working with average cost and average marginal cost, and the same for revenue and profit. And we begin by defining if X is the number of units of a product being produced over some time interval. And we already know that the cost function of C of X, well, if we divide the cost by the number of units X, that gives us average cost. And this little bar over the C, that is typical notation for average. In a statistics class, if you saw X bar, that means the average value of X. So C bar of X is the average cost of production. And if we take the derivative of this, C with a bar and the prime of X is now our marginal average cost. And the same would hold true for revenue and profit. So in this problem, it says a small machine shop manufactures drill bits used to. So here we have our next problem. It states a small machine shop manufactures drill bits Used in the petroleum industry, the manager estimates that the total daily cost in dollars of producing X bits is given by this cost function, C of X equals 1000 plus 25X minus 0.1x squared. Part A asks that we find the average cost of production and the marginal average cost of production as functions. So C bar of X is equal to C of X over X, which is 1000 plus 25X minus 0.1x squared all over X. And in our derivative notes for section 2.5, we practiced rewriting these fractions so that we can work with them on a term-by-term basis. And basically what we do is we distribute the denominator to each numerator term and then rewrite so that we can use the power rule for derivatives. So 1000 over x can be written as 1000x to the negative 1 power. We see that the x's cancel in the next term, so we have plus 25, and then minus 0.1x, because we have x's that cancel again in the next term. This function represents our C bar of x, which is our average cost of production. Next, we are asked to find C bar prime of x, which is the marginal average cost of production, and we use the power rule. Negative 1000 x to the negative 2. Constants have derivatives of 0 minus 0.1. And we can rewrite this as negative 1000 over x squared minus 0.1. So those are our answers to part A. Part B asks that we calculate some of these numbers with the functions we've generated. C bar of 10 is telling us to plug in 10 for each of our C bar of 10 is asking us to plug in 10 into our average cost function. And when we do so, we have 1000 over 10 plus 25 minus 0.1 times 10. C bar of 10 gives us 100 plus 25 minus 1. We get $124. $124 is the average cost of each bit when we're producing 10 bits. Marginal average cost at 10 would give us negative 1000 over 10 squared, so that's 100, minus 0.1. C bar prime of 10 would be equal to negative 10 minus 0.1, which is negative 10.10. And what this negative 10.10 is telling us is that the cost per bit is decreasing by $10.10 per bit at this production level. Part C says use the results in Part B to estimate the average cost per bit at a production level of 10 bits per day. And we would say $124 minus $10.10 gives us $113.90. So we use the average cost per bit and how the cost per bits will decrease with the production of the next bit. And this is approximating the average cost per bit when production level is at 11 bits per day. So this is the end of the lesson. So you can rewatch it, take your notes, complete the practice, and come to class with questions.